Tonight we're going over Bread's 5940's 2023 robot. We're not going to go through the entire game animation again. We should have seen it from one of the other videos, but just the quick refresher, this is the game where they're picking up cubes and cones and replacing them on the grids at the end of the field. And then we have to balance on the charge station at the end. Bread had one of the best robots of the year in this game. They are able to play the game in a lot of different ways. And so we'll watch a video, one of their matches, and then we'll look through all of the different mechanisms and see like kind of some of the unique ways they were doing things in this game. This is one of the final matches at one of their regionals. I think Bread's down here in the corner for the start for Aton. A little quieter. Yes, they're working with Madtown 1323 to be able to go get game pieces and get them back to the grid. They had an intake that largely for cones they were grabbing from the single feed station, and then able to very quickly extend out and get them onto the posts. And so they're focusing mostly on cones while Madtown is doing a lot of the cubes here. I don't think we ever see them ground in take a cone in this match, but we'll look at that in the CAD file and how they're able to do that. But they were able to ground load both objects and human load both objects. They could also get the cone from the shelf if they needed to, from the double human player station. So they had an incredibly versatile robot. It was able to play the game in lots of different ways. I also don't think we see them throw cubes, but that was one of the things they were able to do as well. Their little arm up here could toss the cubes a little bit as well. And so then they also had a unique, one of the more unique endgame mechanisms. They were able to use forks to be able to pick themselves up and like hang off the side of the bridge. So it's one of the more complex robots of the year. It had quite a lot going on in it. So as we look through the robot, it's again going to have a somewhat standard um, look. And whenever we're coming in and looking at robots, we always kind of like break down the mechanisms. They do it in a similar way to what we do. They have numbers and all their mechanisms and things. So they get the drive base here, which we don't have to go too much in detail. We're kind of standardizing in FRC now across drive bases. There's a lot of little details and things, but for the most part, teams are going to have um, a rectangle or a square with the swerve modules mounted into the corners. Here they're using the West Coast Products Swerve X modules. So they have a little bit of a different base plate than like the Swerve Drive Specialties ones. But for the most part, they're all doing about the same thing. They just do it in a little bit different way. So they have a belt here instead of a gear and a few other things. But you can kind of, as you look through them, there's more this year than there ever have been in kinds of different types of modules, but it is useful to kind of have an idea of what they are. So as we're scouting and things and we're looking at other robots, we know a little bit about what they're doing. The other part of their drivetrain, they do have some undermounted electronics. So we can see that they have some polycarb plates here that they have to take off if they need to get to their RoboRio or their power distribution hub. Um, and that's all that's in CAD, but there may be some other things on the real robot. Whenever you have like space like this, there's probably something tucked in there on the real robot that just never got into CAD. It's just room for extra small electronic things, um, switches like the Ethernet switches or power regulators or anything like that can fit down in there. Their battery looks like it does mount in from the top, so it is sitting in here, and they have a little bar that the power leads have to go under so it doesn't end up hitting any of this stuff up here that's rotating. And then it gets plugged in here, so they actually have a little 3D printed block to hold the other end of the connector, it looks like. So we can kind of see that here. So they have this block here that they're going to bolt through the other end of the connector, so it's stationary to the robot, and then they're just able to plug in on top of that. And then they have a very short power path. They have the main breakers right here, PDH is right there. So they have a very short main power runs, which is really good for efficiency. You're not wasting any of the battery power to resistance that's built into the wire. So you always want to keep that pretty short when possible, and have these three things all pretty close together. Okay, the rest of the kind of drivetrain chassis, we have a few different crossbars here. So you have the main ones that are kind of supporting the main run of the robot. They're like elevator mechanism. And then they have these ones out on the side here for the endgame fork climb, where they're able to support themselves on the side of the um, charge station. So going up from there, in their order, they have that elevator. We'll look at the intake first, actually. Okay, so this was one of the more complicated intakes from this year. So it's a slap down style intake, so it kind of starts up and it just has one pivot joint, so it's pretty easy to build. You just have to pivot across this axis and bring it down to be able to go outside a frame perimeter to bring the cube into the robot. But then you also have this roller up here, this extra roller, and that's what's used for the cones. So as this comes down for cubes, it's just going to move the cube in, have it hit the bumper. And then these are mechanism wheels. We've talked about them a little bit in a couple of videos this year, but not a ton. Mechanism wheels or mechanism wheels are a type of omnidirectional wheel that has the rollers at 45 degrees. And what that lets us do is even though they're just spinning along one axis, like if you just had a normal wheel, they're always just going to push in one direction. It allows the object to be kind of moved to the side as well. So for cubes or balls or anything that can kind of be compliant, as this is rotating and spinning in, the cube runs into these wedges here on the side, and it's contacting these wheels, and it allows it to very quickly slide over to the center and get pushed up with this wheel and this like center omni wheel here, and get driven into the claw so it can actually be intaked and taken up to be scored on the higher levels. And so this gets used a good amount in different intakes. It allows you to vector the game piece into the center of the robot. So anytime we have to center a game piece like that, if we need to have it in the center of the robot to score it more precisely, mechanism wheels or vectored intake wheels are always an option. We've run them on a few different past robots. 2014 is one of the first years anyone did, and we developed it and were able to use it for that large ball as well that year. And then that's just going to go up after they have to like kind of have everything in sync. So as they go into cube intake mode, this arm's going to fold back down, so they're in like a certain state that the robot's going to be in to be able to bring that cube in, and then be able to flip it back out when they need to. For cones, they actually grab cones with them tipped pointing away from them. So the tip of the cone is going to be back over here, and like the face flange base of the cone is going to be sort of up on the ground facing towards them. They bring this whole arm down, and the flange of the cone gets grabbed between these two rollers. And we can kind of see the powertrain of this whole thing pretty quickly. it just keeps doing that. Okay, so we have the gearbox here that is driving the actual pivot. And so this is what's pivoting the arm in and out. And then on, let's see if we can get that. Is driving to the shaft itself. And so this is what we call coaxial. So we have these two different belts and they're doing two different things. So this motor is driving the actual shaft and it's spinning these rollers, and then the belt up from here is going to spin this roller, and then they're going to do it again to spin this top roller. And then we can see at the last part of that we have another belt and then some gears to be able to reverse the roller that have these small wheels on the end. Their final like cone suck-in roller are getting reversed by those gears on both sides, so it's kind of redundant here. They're driving it from both sides. And we'll look at exactly why that's happening. So the way it's coaxial though, because we didn't quite finish that, are these plates here and this pulley are all not actually mounted to the shaft. They're just mounted to bearings on the shaft. So if we hide some things, we can see that there's a bearing here. And that is what's actually allowing this whole thing to spin around the shaft. Even if this hex shaft is spinning really fast for the intake, it doesn't change the position of the arm itself. And so that pulley that we hid is bolted directly to the arm. And that's what's giving that whole pivot system, having it work. Same thing down on that side. So it's really only pivoting from this side. The motion down here doesn't seem like it's not powered by anything. It's just giving it an encoder. So they have this CAN coder here. And so this is allowing them to get direct 1-to-1 gear ratio or pulley ratio or something close to that. Those look like the same size. And so that's giving them their feedback for where that arm is positioned and for what angle it is. So they're able to set that angle really precisely to make it the right height to intake cubes or cones. And make sure it's folded back into the robot at the start of the match or when they're driving around. And so the power is actually happening on this side, and that side's just for sensing. Okay, so then that power transmission for the intake is pretty simple. It's just powering those different rollers for the cube. But for the cone, it's a little bit different. You can see this plate here where this whole roller mechanism with the gears and everything is mounted isn't actually attached directly to this plate at all. So this is again kind of free to rotate because it's mounted on a bearing. We can see it come in here. So there's a hex bearing here that's able to spin. And so even though this shaft is spinning and this shaft is spinning, the plate itself can rotate around. I believe this hole here is for some amount of surgical tubing or something to bring it so where it's tensioned down so that this is always pushed up into the right position when nothing is counteracting it or acting on it. So it'd be something here pulling down on this. But then as the cone gets sucked in, so this wheel's kind of turning this way, this roller's turning this way, and then these wheels are turning the opposite way because of that gear stack. It'll actually pull this whole mechanism down further so that the cone is able to get flipped upside down into their robot. If they didn't do that, when they went and intaked it, they would flip the cone over and then they would be upside down when they went to score it. And so that's not what they wanted to do. So then they actually flip the whole cone and the flange basically is facing up towards the sky. And so then when they grab it with their arm mechanism over here, they flip it over again, and then it's ready to be scored, and the base is kind of pointing down, so it can actually go onto the pole. And so they're able to get that like almost extra actuation just from the rotation of this roller, and the ability for this to pivot a little bit around that shaft. They're able to get that extra motion on the cone without having to add another motor or have pneumatics or anything like that. The intake itself is polycarbonate towards the outside, so if it does take a hit, it's able to flex out here, but it's very rigid on the inside here, so it's able to have that, it's basically almost able to transfer the torque and the motion across this 1/4 inch aluminum and this 1x1 tube. So it's okay that they're only powering it on this one side, because you have that rigid aluminum structure kind of down here where it needs to be. And you're going to have this being able to stay pretty straight because of that, because it's going to be really hard to twist anything in here, where if you just had the polycarb, it might twist a little bit more. And so then, since this is pretty short, that square tube, when it's folded out, doesn't stick very far past their bumper. And so if anybody does run into the intake itself, it's able to kind of be compliant, it's able to flex a little bit, and ideally not permanently bend or break, would be the goal. And then they have a couple little guards to prevent the cubes from running into the belt too hard or getting pinched in some weird spot. So they added some bent polycarbonate here, just to prevent any of that. It also probably holds the belt on a little bit, so the belt can't pop off in any direction. And they did, like we already briefly talked about, they did have a gearbox down here to do that pivot, with just, it starts as a belt and then it gets up to gears and then goes back to a chain here. Okay, so moving back to elevator. Let's see if we can, yeah, we can isolate that a little bit, so it makes it easier to see. So that elevator is mounted through that whole main crossbars in their chassis. Let's see what we're looking at here. So there's a few different things that are a little bit interesting here. So it's not the carriage for the elevator, kind of the inside stage that moves, isn't all the way down at one motion, so they can bring this even farther down, and they're not actually, there's not a lot of crossbars on this elevator holding it together. They have this one lower one down here pushed back so it doesn't interfere with the pulley on the wrist mechanism that's able to kind of flip the cubes and cones in and out. So it's just spacered off of here, and is done in a way that allows the bearings and everything to slip past it. So that's why you have these like interesting shaped tubes. And they also did that to give it a little bit more strength. It goes all the way through, now that we can see that. If we make that transparent, we can see that this goes all the way through and then is bolted in to the outer face of this tube and the outer face of this tube on the inside here. And so that's going to be a lot stronger than if you just bolted it straight to this inside face. Let's see. I'll hide that polycarb panel real fast. The elevator itself is using custom bearing blocks, it looks like. I don't think those are COTS in any way. But they are similar to some of the COTS ones, so they have the outside bearings that are riding on it, and then the dowel pin in here with the smaller bearings to ride on the inside faces. It does look like they did some cutouts in the tube, so we can kind of see that. So they have some cutouts here for those interface bearings to go into. Okay. All right, let's see if we can't see the full motion package. So we have these two drums here. So we have a motor on a gearbox that gets belted up to there. It doesn't look like, or is there another one? Yeah, and so then there's another one as well. So they have two motors powering this shaft and pulley, which I believe both of those are all mounted to the shaft. I think. Let's see if we can. Yeah, so all of those are going to be on that shaft. Um, and so they do it using a rather large aluminum tube. Let's see. But it is spinning on a bearing there. Oh, so that's in the plate. That would make sense. So yeah, so then the tube itself here um, likely has some form of press-in hub on the outside there, so they're actually able to rotate it at the same time. I'm not sure we see it in CAD, but it may just not have been CAD'ed. Yeah, it doesn't look like it, but there's almost certainly something in here to transfer torque, right? This can't just be floating in the middle of the air here. So we can go ahead and bring some of those plates back and parts. So that allows them to have this be a very strong tube. You're not gonna bend the hex shaft or anything, so you have the larger diameter aluminum tube on the outside. It gives them something to mount their printed spools to. So we have these printed spools here that look like they're bolted into the tube itself. At least what I think we're doing. Let's see, so we can kind of isolate that. Yeah, so it looks like you have a nut pocket there and potentially a bolt to go through it. I'm not entirely sure what that part is for. It may be for holding the string on. It may just be for how it's constructed. You can see the other side is a little bit different. Yeah, the other side just has the through bore, so they're probably coming through and going back into that lower side. Yeah, they could be bolting through that. That could be for the string. And they're able to get that mounted. So these are all rotating together on that shaft the whole way through. All right. So with the string, they are using that to wind and unwind and actually lift the elevator. So you can kind of see where the pulleys and things are. They have them running inside of their tubes. So you have like a pulley here that string's going to run around and go back up the that elevator with. And since it's just a string, they're able to kind of redirect it. So even though the spool is going this way, the string itself is going to start redirecting around this pulley right here, and then it's able to go down the whole system again to another pulley and come back up to this pulley up on top there, and then down again to be able to pull and push the carriage up and down that elevator. So you do have to make sure, so they have like the windings in here that are printed in so that the spool should be able to be very even as it's going in and out. It shouldn't be wrapping on top of itself. You'd have to be careful with things like that because if it does wrap too big, then your pulley diameter is bigger. And so you don't actually know exactly where the elevator is. If for some reason it's wrapping too fast, you may be moving more than you think you are. And so you want to be careful with that when using string in an elevator. Let's see. The tie point on the carriage should be down in here. Or did they do a full, is it a continuous string? It might be. I can't tell. So they have the pulley there. Somewhere they should tie it off to the carriage so they can actually pull it up and down. It doesn't look like it's going to be easy to see that. Let's see. So on just elevator, maybe be able to see it a little bit better with the path of the pulley here. Let's see. So it's going up that one like we talked about. It's going to change direction there on this pulley. Let's see, it's probably farther down. Yep, so there's a down pulley that it's changing direction again and coming back up. And then it looks like that's going to have it come down. And it may just be going around that. Let's see. Yeah, I don't see anything else in the CAD that suggests why that would be there. And then I'm not entirely sure why the extra pulley is there either, or the extra spool down at the bottom. It may just be for how they're doing things. They may have like a, it's possible that there's two, both of these spools are for pulling it out, and then they may have a central pull back. So like this may be the pull down separate from the two that pull it out. That would be my guess, but I'm not sure how that would run if they do that. It may not be in CAD, or I may just not be seeing it. So this would be a cascade elevator, or sorry, not a cascade, a continuous elevator. I said the wrong word, because you have that one string going all the way through the mechanism, or all the way through the stages at least on the up pull. Let's try to get some of our elevator back in place. Okay, and then the other part of the elevator that they use, they have these constant force springs that are helping assist the lift, so the motors aren't having to do all of it. These springs get tied down, likely down into here. Yeah, so this bolt point here is likely for that constant force spring. So it's always trying to be extended. So it's helping pull against gravity, and so the motor has to do less work since the spring is always trying to feed it up. So that allows you to have a more precise system, and just use a little less battery power to actually raise your lift. And then when you go to power it back down, it's a little bit more controlled because you don't have gravity trying to shove it down the entire way. In the carriage itself, they built in the mechanism to actually power their wrist. So we have this little cover here to make sure that the cones and cubes don't go into this power part of it, I imagine. So it's bringing up, they're able to have something rest right here. We can go ahead and hide that so we can see that power transmission part. All right. And so they have a compound sets of belts and pulleys. So they have a motor here with a pinion on it to a bigger pulley. I imagine that's printed. Yeah, so it's probably printed, so it has this 3D insert, steel insert into it or aluminum insert into it. And so that's able to go on the hex shaft that's here, and then they have this larger printed pulley with some weight reduction or strength as well, so you get those walls printed around there. And then again to another pulley and another pulley set to get some more reduction. And then double pulleys up here at the top to mount the actual arm. And if everything is printed, you can do this. If they're not printed, it depends on whether these pulleys are actually keyed together at the hex shaft. Depending on how the hex goes through, sometimes or how they actually put the hex into the part, you won't have them keyed off anything. So then if the hex and the pulley teeth themselves won't align between pulley and pulley, even if they're the same size, and you can end up having a place where like the teeth won't actually mesh correctly when you have two on the same thing. When you print them, you don't have that problem. And a lot of the manufacturers of cots over the last like 4 or 5 years have started manufacturing them in a way to where they are keyed, and they'll have a little notch on them, and so you can know which side is actually going to be the same across two pulleys. So you can put that same notch on the same face or the same corner of the hex shaft, and that allows you to line them up and make sure the whole system's going to work properly. So anytime you have two chains or two belts, or even two gears going to this from one shaft to the same other shaft, you do have to take into account whether they are all going to be the same with that hex bore on the inside. It is a little bit easier now because more manufacturers have started doing that. Before, you used to just have to like buy a bunch of the pulleys and try to find ones that were close enough, or the same with the gears, and that was not the most ideal way to do it. And again, if you're manufacturing your own, if you're printing your own, it's pretty easy to get those to line up since you're all printing them from the same file. Okay. The wrist tube itself, they went ahead and lightened quite heavily, so there's not a lot of material left in here. They cut out quite a lot of it to make this really light. And then up here, it's pretty simple intake mechanism. This sort of Y gripper is used a decent amount. This is sort of any of the horizontal intakes, or um, hug intake, or however you want to call it. So it's grabbing the sides of the game piece. They use a motor and a belt to start it, and then they have two gears here to do the reversing of direction. And then it's just belted out to each of their wheel sets to actually get power here. So they have the inner wheels here that are going to pinch the cone really hard. And then they have these small wheels up here that are basically designed to grab the cube. And then these outer wheels are mostly for centering either the cube or the cone as it's coming in. So if the cone hits off at a side, it's able to get sucked into the middle here. Relatively easy. Or if the cube got hit weird, it could also get bounced into the middle and then get grabbed up by these correctly. I think that's the majority of the elevator. This mechanism doesn't have to be all that strong. It should never be hit by any other robot, right? It is an intake, but it's pretty much only leaving their frame perimeter when they're in those two protected zones, either in their loading zone area, or if they were in their scoring zones, is where you're going to have those game pieces, or you're going to have that deployed and actually being used. It is all just polycarbonate here, it looks like. And with basically live axle everywhere. So they just have the hex shaft spinning in bearings on those plates all throughout this setup. And then they did even go out and make it even lighter, so they did pocket the insides here. So all of these are cut throughs to just a thin area up on top or bottom to make it even lighter as they were moving that, so then they can move it super fast. If this whole mechanism is pretty light, you have less mass that you're actually moving. And also there's just a lot going on this robot, so they probably just needed to get down on weight as well. And so they were taking out weight anywhere they could to make sure they could be under the weight limit. Okay, I don't think I missed anything before we start going into the system. So I believe they have a few of these different cameras that are for localization as well, likely running photon vision or something similar. And then they also have, let's see what we can do. There's a limelight here. I think it's mounted upside down in CAD, but that's fine. That I believe they were using to detect the cone positions and things when they were going to actually score. And so they were able to use vision to automate a lot of their robot processes. It was basically what everybody was doing that year to try to make it as easy as possible to score cubes and cones on that grid without having to have the drive team align it perfectly every time, because it was a relatively small um, scoring box, especially for the cone, getting it onto that pole. You did have to be pretty precise, so getting it there quickly and using some automated sensors for that was really useful in 2023. All right, so I'm going to hide the drive base real fast so we can kind of see into here. So this is their climber fork mechanism. There were a few other teams that had a similar style forks. The idea being that if you could have a heavy enough robot out far enough at the edge of your fork, they would have more leverage. So as you lift it up, either raised vertically or kind of tilted, or in this case for bread, they actually end up doing a little bit of both. You get your robot fully off the ground, and that was all you had to do to be counted as on the charge station. And then you had a lot more room for your other two partners to be there if your robot was hanging all the way off the edge. It did take a little bit of time, but there were some times where it was faster because the other two people could be already balanced and you could drive in. And so it did work out for some teams, but it definitely wasn't necessary to be able to win matches or anything in this year. Okay, so let's see what they were doing to actually be able to power this mechanism. So they have a Falcon going into a Versaplanetary. So this is giving them some amount of reduction here, anywhere up to 10-to-1 reduction in just this small planetary, to a few more gears, because they do have to, this whole mechanism is going to have to lift their robot. So it needs to be geared down quite a bit to have enough torque to where it's not spinning that fast, but it has a lot of force to be able to actually pull their whole robot up. And so they have the gear going to here. There should be, yeah, so the gear goes from the motor to this large one, the small one on the outside to another large one, and then we get, what's the easiest way to see into there? There's a lot of robot in the way. Okay, I'm gonna hide that gear, and that should let us do it. All right, that's enough-ish. So then there's gear into gear, and then this hex shaft is your main driving source to kind of output that power to both sides of your fork mechanism. And so this ends up being a sort of a version of an elevator or a climber, right? So it's really doing is pulling down on some string, most likely. So if we're looking here, actually there is, that's part of the cam, but I don't think that's the only thing powering it. It might be. Let me see if we can get a little bit further into this. Hide that. Okay. Let's see. So I don't know why I keep zooming out. There are this block up here is for a constant force spring, I believe, to pull up on this whole sled. So you have the bearings here and in here on the side. So as this whole sled goes up, that's how they're able to get they're able to get high enough to be on top of the charge station. So you can kind of see it here. They have all of these bearings riding on these tubes. And so that whole mechanism is able to go up. The trick is how it all comes back down. And so it looks like that's just part of the release here. So at the start, this is kind of turned on and holding this in place so that this can't flip out. And so as this rotates, this is able to spring around and this gets pulled up and folds out. So this whole part is going to go that direction. So it's pivoting around this large shoulder bolt right here is what it looks like. Um, let's see. So as it does that, that's going to come out. The whole thing can rise. And then somewhere in there, I believe it's going to run into something else, but I'm not entirely sure where. That's what I think happens, because somehow they get that little angle tilt at the end as well. So you can kind of see the latch here and what it's latching onto. This comes out, and then that can go up and extend. Let's see if we can. Oh, well, that's a whole internals of a limelight. All right, that didn't help me much. How does it do that? So it, okay, so does that come all the way back over? It might. I'm not entirely sure how the cam portion works. So somehow as it's pulling down, it also tilts them up a little bit. I'm not sure if we're seeing it in CAD or I'm just missing it. I might just be missing it. This is not a native Onshape file, so we can't rotate things and actually move it around as easily. That would likely help for some of this. My guess is it might have to do with the shape, but that's part of the moving part. So that's going to go and get kind of caught there. So when that pivots off that point, this kind of rod gets caught in to the back of this point, I believe. So I think that's why it's kind of cut out like that. That's going to nest there. So I believe that's what happens. It may just be here. So as they're pulling down to be able to have this come further down, this may just ride across this side bit here, but I'm not sure. Um, because if this is coming vertically, that would basically push the robot out and up. So that may be what's happening. So I think this might just be riding down this slope so that as they pull fully with that gearbox and they basically just pull down on a string, it's basically level until this part that's folded out runs into this wedge, and then the kind of the back edge, this farther side of the robot, is going to tip up into the air because you're assuming this is going to stay flat on that platform since it's being held down by their partner robot. That's my best guess as to what's happening in this one. I don't see any other way that it could happen, but I may just be missing what's going on there. It doesn't look like anything else quite runs into it or is going to be able to give it that angle. That's going to change that robot, kind of change its lean anywhere. Okay, we can go ahead and put the drivetrain back in. I'm going to hide, can I hide bumpers? Maybe, there we go. Okay, and so on their actual frame, we can see their bumper mounts, so they have them kind of built in to some of their like intake supports here. They have aluminum plates that mount to the frame here and hold up these 2x1s over their swerve modules. So instead of having the sort of mounting rail, mezzanine rail, or anything like that going all the way across, because it's harder to do with this swerve module in particular. Kind of runs out into the sides a little bit more. So they're able to build in this same sort of bumper mounting that 971 started in 2019, and then several teams have done since then. And so those plates get machined, and as you set the whole bumper assembly in, you just tighten up this nut here on each one of these corners, and you get secured bumpers that way. You can see they did some like nice cutout thing. Oop, that went a little too far. So this kind of round out here is a dog bone or overcut. So they overcut a little bit to where you can fit that whole square corner into those edges. So this plate gets a little bit supported by the top as well, not just the crossbars here or anything. They're able to do a little bit more there for it, and they make these blocks that are able to tap the bolts into. So these are possibly I'm guessing these are probably aluminum to be able to hold the entire robot up. And so they probably just milled these to be able to support this whole plate and mount it into that frame rail. Their forks themselves, we didn't really talk about. Those are just pieces of 2x1, relatively simple, with some angled ends to help them get under their partner robots. So this is just 16th wall aluminum tube, so nothing too special there. So as long as the team they're driving under had an inch of ground clearance and a relatively solid belly pan, they're able to slide these under and then lift themselves up onto the edge of that platform. What did we not see? Can I? Okay, it doesn't look like they sub-assembled anything else past that. Yeah, so you can't quite see any of the places where they're like, there's no specific call out for like a tied down string or anything. But it could have been anywhere in there. But yeah, so they have quite a few milled aluminum plates to be able to get all of that geometry, to get all of those bearings into that mechanism. And pretty much the entire, quite a bit of the robot is done that way. But as you are building up things that have to lift the entire robot, things do get a little bit thicker and a little bit stronger, just so they're not flexing under the weight of 140, 150 pounds as it's starting to move around. Okay, I think that finishes it up for today.